Let's take another look at the Atwoods machine. That's two masses hanging from either side of a pulley. This time, though, we're going to put one of the masses on a frictionless ramp and see how things change. Alright, so in an Atwoods machine, you want to be able to solve for acceleration and tension. I'm going to go ahead and solve for acceleration, and we'll see how I can just plug in to get tension. So, to solve this problem, I'm going to need a free body diagram for every mass, but before I do, I'm going to note this little trick. I'm going to call this the positive x direction. Okay, we mentioned this in the other Atwoods machine video. What that means is that for the free body diagram of M1, my positive x direction will be down, and in the free body diagram of M2, it will be moving along the positive x direction as well. Let's see. Like so. Alright, so let's put in the forces. For M1, we have tension in this direction, and M1 times G, the gravity, in that direction. For M2, well, it's sitting on a ramp right here. It does, get that X out of the way, it does have tension, the same tension pulling that way, because this is one rope over a massless, frictionless pulley. So this tension attached to M2 will be the same as the tension attached to M1. Alright, so M2 has that tension. It also has gravity pointing straight down, and normal force from the surface of the ramp pointing straight up. Alright, so I can see our analysis of M2 is going to be a little bit more complicated. In fact, I'd better finish my coordinate axis. I'll call this the positive y direction for M2's free body diagram. Alright, so we will now write our Newton's second law equations. We wrote a free body diagram, so that's the next step. For M1, I have the sum of the forces in the x direction equals the mass M1 times acceleration, and that in the x direction, and that will be equal to M1g minus t. M1g is in the positive direction, t is in the negative direction. So I'm getting that M1 times ax is equal to M1g minus t. Now I'll go ahead and just skip the equation in the y direction for M1 or the other direction because there are no forces in that direction. Okay, over here for M2, it's going to be a little bit more complicated. So remember our angle is theta there. So let's see, if I break my mg up into x and y components like this, that puts the angle theta right in that corner. Feel free to prove that to yourself with annoying geometry. So now I can see my x and y directions for M2g, but I see that my normal force is already in the y direction and my tension is already in the x direction. So the sum of the forces in the x direction is equal to M2 times acceleration in the x direction, which will be equal to, alright, we've got t in the positive x direction minus this component here, this M2g x, and that's going to be equal to M2g times the sine of theta, if you do the right triangle trigonometry. Okay, so this now we'll do the sum of the forces in the y direction is equal to, well, M2 times acceleration in the y direction, but as you can see, it's not flying up into the air and it's not bashing in through the ramp. The sum of the forces in the y direction is equal to 0. It's not moving. Alright? It's not accelerating. So that's 0, but it's also equal to, okay, n is in the positive y direction minus the other component of gravity, M2gy, which is M2g cosine of theta. It must be the cosine if the other was the sine. So this equation is pretty much just telling me that n is equal to M2g cosine of theta, if I even needed to know that. Alright, now we were looking for the acceleration. I call it A, but what I mean is the acceleration of this block down and this block up. They will be equal, and that is for both of them the positive x direction. So I am actually looking for ax. Let's find this ax then. Well, I see that I do have two equations and two unknowns. So if I look at the sum of the forces in the x direction from m1, m1ax equals m1g minus t. And I also have from the sum of the forces in the x direction of m2, m2ax is equal to t minus m2g sine theta. So my only unknowns here are ax and t. So actually I didn't need the sum of the forces in the y direction. If we had had friction, we would need the normal force. But this is a frictionless problem, so in that case that was just good practice. I meant to do it. Alright, so to solve this equation for the two unknowns, I'm going to use the method of addition, which usually works nicely in Atwoods machine problems. If I add them up, I get m2ax plus m1ax is equal to m1g minus t plus t minus m2g sine theta. Negative t plus t is gone. And so to solve for acceleration, I will factor out the acceleration. And while I'm at it, I suppose I'll factor out the g on the other side. Dividing over that. Alright, so similar to the previous Atwood machine problem, we're getting that the acceleration we see will be a piece of gravity involving a difference of masses over a sum of masses. The difference now, with a ramp, I have a sine of theta sitting in there, and the angle would have to do with how fast it would accelerate, and so here's how the angle comes into play. Now to solve for tension, well, I just take either of my other equations here, solve for tension, and plug in the ax. So from the top equation on the screen up there, I have that t will equal to m1g minus m1ax. And so we could plug in m1ax right there, or plug in ax, and we would also have t. So that is a Atwoods machine slightly modified so that one of the masses is on a ramp. You could have friction on the ramp. You could have it on a flat surface with friction but no slope. There's a number of different ways you could set up an Atwoods machine, but the problem-solving method is going to be the same: a free body diagram for each mass, and define your coordinates so that they both accelerate in the x direction.